Alrighty guys, so thank you for joining me on this new Cadence video. So this Cadence video again is built for Texas Tech University class, Introduction to VLSI Design, or ECE 4310 and 5310. But this is going to be kind of a continuation of the series we've been doing the past couple of weeks, where we've been exploring the GPDK 45 nanometer process and also showing you how you can get started with some basic schematics, simulations, symbols, and things like that. Now for this video, what we're going to do is we're actually going to extend an existing schematic that we've already made into something that can actually be fabricated on chip. So we're going to extend this schematic into a layout. Unfortunately, if you just try to send schematic files to a foundry or a fabricator, they would pretty much laugh you out of the room because you actually have to show them how you want the physical transistors laid out, how you want them interconnected, what layers you want them connected on, and things like that. So today we're actually going to look at how we can implement a physical layout in the GPDK 45 nanometer process, and also look at the Assura tools, so Assura Design Rule Check and LVS. And that's just, again, a tool that we can use to make sure that we're not violating any rules set by the foundry, and also make sure that our layout does indeed match the functionality of our schematic. So if we, for example, forgot a connection or something like that, LVS will actually show us that we forgot a connection, which is very useful for these layouts because they can get fairly complex. So today what we're going to do is we're going to look at laying out something like this simple inverter. So we made this inverter here in the past, just two transistors here. This PMOS transistor isn't balanced, but that's going to be okay for us because you can very quickly change the width, and I can show you how to change the width in the layout in order to match the correct width that you want. Now, what we're going to do for this is I'm going to start off showing you how to do a layout and then show you kind of the functionality of the layout and how just a small layout like this inverter can be used in larger logic units in order to actually accomplish more complex tasks without actually having to individually lay out each and every single transistor. And then we're also going to take a look at those Assura tools like I mentioned. So we're going to start off just from this schematic, and this is a very simple schematic. We have just a single NMOS transistor and PMOS transistor, and we've seen in the past how we can simulate this schematic in order to actually make it verify that it works as an inverter and that it works as intended. But now what we're going to do is we're going to actually convert it into a layout, and much like the symbol, the layout is going to be another cell view that's attached to this inverter cell. So every cell kind of has three main building blocks. It's going to be a schematic, a symbol, and a layout. Schematic is where you actually implement with subcircuits or with transistors what the functionality is. The symbol allows you to use that schematic in larger schematics later on down the line. And then the layout is actually going to be the physical layout of the device. So we're going to start off just like we did with schematics and symbols. We're going to go to File here in the Library Manager, and then we're going to go New, Cell View, and then I'll bring this back over to the screen where we can see it. And the cell view that we're going to make, we're going to keep the cell name as inverter because we want it to be attached to that same cell, the inverter. And this time we're going to change the type to a layout. So we want to make sure that view says layout and the type is layout here. And that's going to actually make it to where we are doing a layout. And it tells Cadence to use the layout application in order to open it up and run it. And then we can just press OK. So you may have some issues with some licenses. Press enter with this. As long as you have your licenses set up correctly, it'll eventually find the one that you need. Now it's going to open up this blank screen. I can press F to bring everything into full view. And one thing I want to go ahead and mention is that in the layout, a lot of the hotkeys are very similar to the schematic, but some things are different. And I'll try and highlight what's the same and what's different in this video. Now we can see it looks very, very similar to the schematic, and it kind of functions similarly to the schematic. We have a grid, we can zoom in, zoom out, and things like that. But first thing we need to do whenever we're making a layout is going to be to add the instances of the devices that we want. So if I look back at the schematic, we know we need an NMOS transistor here and a PMOS transistor here, and they're going to be connected together at the gates. The drains will be connected to the output, and then the body and sources are going to be connected to ground and VDD respectively for the NMOS and PMOS. So we can jump back over to this layout, and we can just start laying down these different devices. So in order to lay down a device or create an instance, we're going to use the I key here, and it'll open up this window here. So right now I have this auto-filled with a different process because that's what I've been using previously, but we're going to make sure our library is GPDK 045, and then we're going to start off with the NMOS. So if we start off with the NMOS, we want the cell to exactly match the one that we have in the schematic. So that's going to be NMOS 1V, and then for our view, we just need to make sure that it's layout. And now we'll see it has a little picture up here for us just to kind of show what we're making. And if we look in our schematic, we can actually place this down somewhere. So I'm just going to place it down right here for right now. Press Escape to get out of the instance tool. And then if I press F to zoom in, we can see that it's kind of just a red square. And this red square doesn't really give us a lot of information, right? Because this red square is kind of missing out on some things. So we can't really see the features, where the drain source connections are. We can't see where the gate connection is. So for us to actually see more detail, we need to actually show the full view. And for us to do that, we have to do Shift and F. And you can do Shift and F right at the beginning, and I'll actually show you all the details of this transistor. And just to verify, let's go back to the schematic and look. This NMOS here is NMOS 1V, and we just want to make sure that everything matches it exactly. Okay, so NMOS 1V, if you use it in your schematic, you have to use it in your layout as well. So if we pop back over to the layout, we can see that we can kind of identify a couple of features here. So maybe these are our two source and drain contacts on the right and left hand sides, and then running down the middle, this is more than likely our gate. But just looking at this, it may be hard to tell immediately what everything is, especially because we kind of have these yellow and red boxes kind of surrounding everything. So one of the first things I want to show you about this layout view is going to be on this left-hand side here, this layers window here. So if we take a look at this layers window, there's a lot of different stuff. We can kind of use our intuition to figure out what some things are. So here we have something like metal 1, here's the drawing. And if we use this NV up here, it stands for no view. So AV is all view. It turns on all the layers so they're visible. And this NV is going to be none visible. So it's going to turn off all layers except the ones that we have selected. So since we've selected metal 1, if we press NV, it's going to make all those other layers disappear. And we can see that this is indeed a metal 1 trace right here. So this is kind of either the source or the drain contact for this NMOS transistor here. Now we can kind of play around with these different ones. So this CONT is a contact. It's going to be going from the metal 1 layer, so going from a higher layer down to a lower layer. And then we also have metal 2, metal 3. We have a lot of different metal layers here. We also have this in-well layer up here, but we can't really see anything with it right now because we don't have a PMOS, and an NMOS doesn't have an in-well. So we can kind of use this to just sort of, to kind of figure out what these different layers of the transistor are. So I'm going to go ahead and put all view back on. And just to show you a resource, so this PDK actually has a lot of documentation. So if we take a look at this guy right here, we can take a look, and what we'll see is that it has on page 7, of this GPDK 045 DRC document, it actually describes all of the different layers. So if we go to page 7, that probably won't work here because it's off numbered a little bit, but we can scroll down to page 7, and it actually shows us all the device layers, all the routing layers or interconnect layers, and all these other different layers. Okay, so DRC, LVS, marker, and label layers. Okay, so we can kind of see we were kind of correct on some things. So we have our in-well is an actual in-well here. In-imp is going to be the in-plus implant, so that could be like the contacts for our NMOS transistor. And if we go back to Cadence, we can find in-implant right here. And if we make no view, then we can kind of see this is going to be the in-implanted region here for our NMOS transistor. Okay, and if we have some other high or low threshold voltage NMOS here, this would kind of highlight it here. So this can be a very good resource if you're trying to figure out what exactly is going on inside this transistor. Kind of similarly, we also have an oxide. So if we turn on the oxide layer, we should expect that there's going to be an oxide that goes underneath our gate. So our gate, we don't want it to be connected to anything, and this is that oxide layer that's going to be making sure that our gate is not connected electrically. Okay, so I'm going to go ahead and set all these layers visible again. And then we already have our NMOS laid out. I'm going to try and get it centered as best as I can. So I'm going to select the NMOS, press S, that's the stretch tool, and we can kind of move it around a little bit, but I can go ahead and tell you there's not going to be a way that we can perfectly align it to the center line here. So for me, I like to align them to the center line as much as I can, but we can see it's not going to be all the time possible. Okay, and that's totally fine. Now we have our NMOS laid down. Next thing we need to lay down is our PMOS. So I'm going to press I again, open up the instance window. I'll bring it over here so you can see. And instead of NMOS 1V, we're going to do PMOS 1V because that's the same one that we have here. And now we can set this PMOS down. I'm going to try and get it as lined up as I can again, and we're going to set it down right here. Press escape to get out of that. Now I can see it looks very, very similar to the previous one, but what we have here is now we have an in-well inside this PMOS. So a PMOS has to have an in-well in order to actually be created. So because of that, we have this in-well here. So we're creating an in-well in the fabrication process, and that kind of tells us that this is a PMOS. And again, you can look through all these layers if you kind of have more questions or are curious about anything. So like this P implant shows that this is the P plus implanted region. Okay. And again, this DRC document is going to be very, very handy. So like P implant here, we can very easily see it's the P plus implant. Okay. And then polysilicon, let's see, there's a couple of other like active areas, things like that. in wells, but a lot of this, we're primarily going to be using some very simple ones, okay? But you can use this as a reference. So if we go back to our layout, first thing we can do is we can go ahead and connect these gates together here. So these gates are formed by this polysilicon layer. And what we can do to actually connect them together, we could try and just create a shape and a rectangle, and we could try our best to kind of get it lined up here. But you can see we're not ever going to be able to get it perfectly lined up because our grid spacing doesn't exactly match the one that they used when they were creating this transistor. Okay, and that's totally fine. So what we can do actually, instead of having to draw a rectangle, we can actually select the layer we want. So whenever you're doing any sort of routing or drawing a shape or anything like that, you need to make sure the layer is selected on the left-hand side. And we're going to draw a shape on the poly layer. Now, instead of drawing a rectangle, what I want to show you is how you can actually draw wiring, because that kind of makes things a little bit easier. So you can either go to Create, Wiring, and then Wire here, or you can just use the hotkey P. And I like to think that P stands for path. So if we go right to the edge or just right inside of this polysilicon line, we can press P. And we can see that the path tool is opening up, or the wiring tool. And then if we click down right here, it actually automatically selects the poly line, okay? And one thing that we'll notice, it tries to match the width as much as it can, but as we'll see, if we lay this line down here and we try and scoot it over, there's never going to be a way for us to get it aligned exactly. So that's just kind of a limitation that we have, and we're going to have to work around, but like I said, that's totally fine. So what we can do, if I lay down this poly line, I can press Q, open up the properties window, and if I want to change the thickness of it, I can do that right here. So I can change the width to maybe be 0.06. We can press apply, and now we can see that's actually increased the width of it slightly. So maybe now we can scoot it over just a little bit in order to help it get a little bit more aligned here. Okay, so we can try and scoot it over as much as we can. Yeah, and so now we have it pretty much as close as we can get. So we have a little bit of excess on the left and right sides, but that's okay. Okay, so this is one way that you can do path, and it actually works the same way for the metal layer down here. So if you're trying to be as complete as possible, you can actually select metal 1 and then press P. Click down right here, and then it'll start your metal 1 path. But like I said, if we still have poly selected and we come over here, press P, and are trying to route the metal 1, it'll actually ask us which one we want it to route because it couldn't find a poly layer. So it's going to ask, do we want to do a rectangle on metal 1 drawing or a rectangle on the oxide drawing? And we definitely want it to be on metal 1. So we can either click this guy right here, or if you're more color oriented like I am, you can just click the blue color that we know corresponds to metal 1. So you can click that there, and then you can begin routing here. Now, one thing you'll notice is that it actually starts telling us the minimum area, and that's one of the design rules that are built into this process. So every layer has to have a minimum area, and that just helps with the reliability and the yield during fabrication. So we need to make sure that if we're trying to draw this metal layer, that we're satisfying this minimum area. But what we can see is we don't have to bring it all the way out to here. We can actually just stop here. If we click, it'll create a junction, and then we can begin routing all the way up to here. And now we can actually create a contact on this PMOS here. So this can kind of be our drains. So if we call these our drains for the NMOS and PMOS, this is now our output here. So this is where our output signal from our inverter is going to be. Okay, so now let's do something similar for this input here. So we could keep our path on polysilicon, but generally it's a better idea if you actually make it into a metal layer, because the metal layer is going to be more conductive, better performance. So what we can do is, we're stuck on polysilicon here right now. We actually need a way of jumping up into the metal 1 layer. And that's actually very simple to do. So we're going to have to use something called a via. So using a via is actually very simple. So you can either go to Create and Via here, or you can just press O. So if you think of a via as like a hole between layers, oops, accidentally opened help. If you think of a via as a hole between layers, the O key kind of makes sense. You can just press O. Now, thankfully, we already have the metal 1 to polysilicon via opened up. But if this wasn't correct, if we had maybe like a different via selected, we can actually use this via definition here to tell it what we want it to go to. Okay, so if we want to go metal 1 to poly, we would select M1_PO, metal 1 to INWELL, metal 1 to PSUB, implant layers, anything like that, or metal to metal vias. One thing you can also do if you need to go from like metal 1 to metal 4 for some reason is that you can also create a stack. And then you can set a start layer. So for example, metal 1, an end layer all the way to metal 4, and then you can specify the rows and columns and things like that. And it'll actually make a whole stack up of vias for you. But ours is very simple, so we're just going to use single right now. So we can see here that our via only has one contact, And that may not be super good for us because we want to make sure that it's a very strong connection. And if this contact doesn't come out well during the fabrication process, then this inverter just simply isn't going to work. So what we can do is we can actually add a couple of columns. So if we make this 3 columns, then we'll see that now this via is a 1x3, has a 1x3 layer of vias that we can just click down right here. So now if we look at individual layers, we can see that there's a layer on poly, and there's also a layer on metal 1 that's right on top of this guy. And we also can take a look at the contacts, and that's going to show us that we are indeed going from the metal 1 layer down into a lower level layer, and in this case it's polysilicon. And this is actually going to electrically connect whatever is on the metal 1 layer here, so our input, down into this polysilicon gate. Okay, so I'm going to set all view again. So now we kind of have something that's starting to resemble an inverter. And this isn't something that you necessarily want to only rely on in the beginning. That's definitely something that you can use throughout the entire process, but it's good to start checking your design rules earlier rather than later. Because if you design something more complex, like maybe like a D flip-flop or something, and find out that a lot of your rules are violated, you may have to completely relay everything out. And that can be kind of a pain. So it's much more useful if you actually check and make sure you're following the rules earlier. So what we can do, since this PDK uses Assura, we're going to come up here to this Assura tab, and then we're going to click Run DRC, and that stands for Design Rule Check. So the DRC makes a ton of files just as log files, so I don't want to have them cluttering up my main folder, so I always make the run directory ./DRC, and that just makes a folder called DRC for all my DRC files to be stored in. And then what we want to do is we want to make sure we're looking at the right cell and view, so inverter and layout in this case. And then we want to make sure our technology is selected as GPDK 045_AV. So this is going to be all the rules for the GPDK 45 nanometer process that we need to follow. Now, we don't need to worry about anything else. We can just press OK. It's going to ask if we want to save the data, so that's probably good. And then it's going to say, for me, I already have data existing in ./DRC, so we're going to override it. But the first time you wouldn't have something like this. Now, this new window's popping up over here, but we're going to see that the results ran successfully. So we can view the results of this run. We can press yes, and I can pretty much guarantee that there's going to be some errors here. So yeah, we can see that there's definitely quite a few errors. And we can see a couple of these. Minimum in-well width has to be greater than 0.3 micrometers. And what's really cool about Assura compared to some other DRC softwares is that we can actually click the error we're interested in, press this right arrow, and it zooms in and flashes on what it is that we're looking at. So in this case, it's our in-well layer here. The width is not large enough, and we can see the area is not large enough too. So we need to maybe extend this in-well a little bit in order for it to be, to follow the rules. In a similar way, our metal 1 area has to be a certain amount, so we can zoom in here. It's going to flash on this metal 1 contact. The area is too small. And then this other metal 1 contact that we haven't routed, the area is too small. Now, kind of in a similar way, there's this other one, maximum distance from any point in a P+ source. A lot of information like this. So this is going to be a little bit more complex. But one thing that's really useful is that we have this DRC document that we can look back at. And what we have to do is we just have to look at the code that's shown here, latch up 0.1. And we can actually come over here, Control F, latch up 0.1. And then it actually tells us a little bit broader description. And it kind of has some pictures too. So the maximum distance from any point in a P+ source or drain active region to the nearest in-well pickup in the same in-well. So this maximum distance is going to be 20 micrometers, essentially. Let's double check and make sure that's right. Yeah, so it has to be 20 micrometers here. And what that means is that we haven't added any contacts in our in-well that have tied like the source or anything like that to the in-well. So there has to be uniformly distributed in-well contacts. They can't be more than 20 micrometers away. And since we haven't added any in-well contacts yet, we're definitely violating this rule. So what I'm going to do is we can come up here, do Assura and close run just to kind of get some of that stuff off of our design in case it's cluttering things up. And we can start by adding in additional area to this in-well. So we know that that's one thing we need to do. So we can add an additional area to this in-well. And the way we can do that is we can just select our in-well down here. We can even go a little bit further out. And then we can go make sure in-well select on this left-hand side, create, shape, and rectangle, or just press R. And now we can draw a rectangle over this in-well here. Now, if we just look at the in-well layer, we can definitely see that there's one rectangle inlaid inside of another, but the DRC and the fabrication team is going to treat this pretty much as one single in-well. So even though this in-well area that we started with is still smaller than what we would need, it's going to pretty much join these two together. So if we do Assura, run DRC, once you have everything set, we can say we want to see this. And then if we take a look at these results, we still have this latch up because we haven't created a contact yet, but we can see that that in-well, we can see that that in-well area has disappeared. So that in-well area error has disappeared. Now, there's also a couple of other ones, P substrate stamp error float. That's probably because, again, we haven't added any contacts to it yet, okay? And like I said, we can look back at our DRC document here. We look up something like stamp. Not exactly in here because we're not following the rules. This isn't a very good design yet, but if we have a better design with some contacts on there, then we should see that it works out perfectly fine. So let's keep going here. So we know that the source of our PMOS needs to be connected to VDD, and the body has to be connected to VDD. And right now we have nothing that's connecting the body or this in-well. Let me close this run so we can get this flashing off. We have nothing that's connecting this in-well to VDD, okay? We haven't defined anything, and it really wants that to be well defined. So what we need to do is we actually need to make sure that this source and this body are connected together. So in order to do that, we're going to use vias again. So I'm going to press O. And the via that we're looking for, so we're going to start from the metal 1 layer, and then we want to go all the way down into the in-well. So we're going to go M1 to in-well here. And because, like I said, we want to make sure that this connection is solid, it's best to have multiple contacts. So we can do something like 5 here. And then we can just set this down right here. Try and get it as centered as I possibly can, but it's going to be okay. We can definitely fix it in the future. So we can set this down right here. And now we can see that this rectangle is kind of protruding beyond this other in-well rectangle that we defined, but that's a very easy fix. So we can just press S for the stretch tool, select this one side of the rectangle that we defined, and spread it out so that it is covered. And this makes a nice kind of smooth transition, doesn't have any jagged edges. Now what we want is we want this source of the PMOS to be connected to this body connection. And we can do that by coming here, pressing P, clicking on this guy, making sure we have metal 1 selected, and then we can just make a route that goes directly up into this contact. So now we have our source is connected to the body, and it will actually automatically find out that this is our VDD connection, essentially. So we don't have to tell it that this is VDD or anything. We don't have to add any voltage sources. Now, if we run DRC again, just to make sure that it's good to run kind of incrementally, fixing things, and I'm doing air quotes around that because sometimes fixing things create more errors. So it's going to run things incrementally. And we can see here that we already have some, we already have some more errors that are introduced. So minimum in-well enclosure of in plus active area has to be greater than 0.06 micrometers. So we can see here pretty much what it's saying. This red is the, the in plus active area here. So if we maybe take a look, should it be under in implant? So we have an in plus implant here we can see. And then we also have, is that oxide in this case? So we also have this oxide layer here. And it just wants this distance to be greater than 0.06 micrometers, okay? And that's why I was saying you can use this to kind of zoom in on what it is that we need to see, and it helps to highlight it. So this is showing this is where the error is originating, and this distance has to be greater than 0.06 micrometers. So if we minimize this, there's another tool that we can use. It's called the ruler or the measurement tool, and you can get to it by just pressing K. So press K, and we can actually measure the distance from this edge, since it's our problem edge, and we can put a little ruler down to show how far away we need this edge to be. And this is really useful because we don't want to keep guessing and things like that. So now I can just press S, select this side here, and just scoot it over until we are at the correct distance. Now we're also going to scoot this one up to the top. And we know that we're violating the rule on this other side as well, so we can do K for another ruler. Stretch it out to 0.06, and then press S for stretch. We're going to stretch this right side all the way towards 0.06. Okay. Now we can go to Tools, Clear All Measurements, or just do Shift K. And if we do Assura, run DRC again, this time, like I said, want to save, press OK. Already exists. You can press. And this is one we haven't quite yet, so it's saying we can't start a new Assura job when a run is currently active. So that's just asking us if we want to close the current run that we have, and we do. So we can just press yes. Now it's going to run. what we can see, ran successfully, check the errors, and now those errors have disappeared essentially. So the errors that we were looking at have kind of disappeared. So we still have a few. So this one, this contact area is a little too small. This latch up, it means that this active area is too far away from the nearest in-well contact, which makes, or sorry, not in-well, from the nearest P-sub contact, which makes sense because we haven't made a P-sub contact yet. And then this is another one that we have here. So the minimum poly to active area space, so minimum poly interconnect to related active area space has to be greater than 0.05 micrometers. So pretty much that may not make a ton of sense, but if we zoom in on it like we have, then what we can see is that it's highlighting this area right here. And this tells us we need to make sure that this active space, this oxide up here, is far enough away from our poly contact. So it has to be 0.05 micrometers. So we can press K, make it 0.05, and we just have to move it up by 1 grid point. So I'll go all view again, click this guy, press S to stretch the entire thing, and then it's just going to move this up by 1 micrometer. And now we can go ahead and get rid of this measurement here. Assura, run DRC. If press other thing, we want to save, then yes, we want to overwrite files, and we want to close the current run. So now I can press enter to view the results, and now, like I said, it's disappeared. So we still have a couple of errors, so we're going to work on those right now. So our couple of errors are more than likely related to the P substrate and this metal 1 contact. So just like how we have this top contact here, let's go ahead and close this run. Just like how we have this contact that's going from metal 1 to in-well, the source of our PMOS also needs to be connected to ground. So it needs to be connected to the P substrate or the body of the NMOS. So what we can do is we can do something very similar. So I can just press I, or excuse me, not I can press O, get out of this guy, press O to open up the VIA menu. And now, instead of going from M1 to in-well, I want to go from N1 down to the P substrate, okay? And we can do something similar, make it 5 columns long, and then we can place this guy right down here. Now we've kind of learned a little bit, so we can take some design considerations early. So we know that the oxide and poly layers have to be spaced apart by a certain amount. So if I press K here, we can say 1, 2, 3, 4, 5. We can go ahead and scoot this guy up a hair to make sure that they are optimally spaced. It's not really optimally spaced. There's not an optimal location for this to be, but it does help it be more spatially efficient. So we're making it as small as we possibly can. We can see that everything's kind of centered as well as we can get it, so that's kind of looking good for us. Now we can just make another path here. So we can make a path on this guy, make sure we select metal 1, and then we're just going to have this connect to this body contact here. So now our source of the NMOS is connected to the body, and like I said before, it will kind of automatically understand that this is supposed to be ground in this case. Okay, so now we can do Assura, run DRC, press OK, hit enter a few times, just save, overwrite, view the results, and this is what we want to end up seeing. No DRC errors found. So that means that the foundry can actually make this design and not have to worry about violating any of their rules, essentially. So they feel very confident that they can make this design and we haven't broken any of their rules. So that's actually a very good sign. So you want to make sure that you're passing DRC kind of from the beginning, because if you have two things that are too close together, for example, it's way easier to space them apart before you start doing any sort of complex wiring here. So for a simple case like this, it's totally fine. We could maybe even optimize the spacing between the PMOS and NMOS a little bit more, but we don't want to get too greedy with it, essentially, because that's going to be a lot of time. So for example, we can check here the distance to the oxide. Maybe we could bring it slightly closer, but it's really not super well known. Okay, so without looking through the document and becoming an expert in the process, it's hard to say without just testing it out. But for you, you can absolutely test it out and see if you can optimize the size of this design a little bit more. Okay, let me double check my notes, make sure we're not forgetting anything here. Okay, great. So we are definitely forgetting a little bit of something. So we've done a lot of DRC and things like that. But what we also need to do is we also need to make sure that this matches to our schematic. Because we could just have two transistors here with the body connections and things like that, but nothing connected together. And that would actually still pass. If we can pass DRC rules, but that doesn't necessarily mean it's replicating what's going on in our schematic. So in order to compare our layout to our schematic, we actually have to use the LVS tool, and that stands for layout versus schematic. And what that does is that will extract the layout, and pretty much what that means is it will convert it back into kind of a pseudo schematic, and then compare that extracted kind of pseudo schematic to to your actual schematic to see if it has the same functionality. Now, the way that we run this is we're going to do Assura and then run LVS, and it's going to have kind of a similar look here. So we want to make sure our library and cells match between these two, and then on the top one we want it to be schematic, bottom one we want it to be layout. Same thing, it spits out a lot of files, so I have it all go to an LVS directory. Run name you don't have to worry about, and same way we need to make sure the technology is defined as GPDK 045, because that will get all the rule files that you need. So we have it set up to where you just have to use this drop-down menu here. You don't have to worry about finding all of these files yourself. So we can just press OK here. Okay. There's already data, that's totally. And then this takes slightly longer because it has to extract it and do a little bit more work. And what we can see here is that we are definitely not matching, right? So it's not telling us anything good, pretty much. We have these warnings. If we look all the way down, it says no extraction problems were detected, but compare problems were detected in a cell. So pretty much what this means is that we have not passed LVS. This does not currently exactly match our schematic. So we have to do a little bit of looking on this guy just to check and see. Now, I like to use this menu here, but there is, if we press OK, a little debug menu that kind of helps you isolate where things can go wrong. But this actually gives you quite a bit of information. So what we can see here, if we look here, there's an unbound pin in the schematic. That's two unbound pins in the schematic that aren't present in the layout. So if we take a look back at our schematic, we can see that we have this in and out pin here. And just like how we have an in and out pin on our schematic, we need to have an in and out pin in our layout. So the way we do that in the layout is actually very similar to the way that we do it in our schematic, just with some slight differences. So what we're going to do here is we're going to go to create, and then we're going to go pin. Now, what's important to note is that you want to make sure you have the right layer selected. So if you want to make a pin on poly, you need to make sure that poly is selected before you start drawing the pin. Same way, we're going to make all of our pins on metal 1 just because it's very easy for us to do that. But if you needed a pin on metal 2, metal 5, anything like that, you're more than welcome to do that. You just need to make sure that the layers match up. Okay, so we're going to make our pin on metal 1. Our input pin is going to go like right here on this input contact, and our output pin can go right here on our output contact. So what we're going to do here is we're going to say our terminal names. We can do it the same way as we did in the layout. We can do in space out to make two pins after the other. And we also want to make sure that we create a label. Now, we can stick with manual here, but if we click options, what we're going to want to do, this height ends up being 1 micrometer, and 1 micrometer is really big when we're dealing with a nanometer scale project. So what I like to do is I like to just go ahead and make this something like 0.1. You can keep the fonts and everything the same, or you're more than welcome to play with it if you want to, but I'm going to keep it as 0.1 and press OK. And now we're going to keep this menu open, and I'm going to come over here. So our first one that we're going to draw is the input pin. So I'm just going to come over here, and you can draw an input pin. I like for it to be flush, but it doesn't have to be because it'll unify everything whenever it does the comparison. So we can just put it right here. You can see we're drawing a metal 1 rectangle. And once I click down over here, it's going to have me place an input or an in label so that we know that this is the input pin. Okay, so you can place the input pin right here. And what that's telling it is pretty much telling it that this is our input, and it allows it to bind to the schematic input very well. So we can do the same thing for the output over here. So since if we take a look at our menu, our in has disappeared, our out's the next one we're going to do. So we can do our output right over here. It's right here. And then we can place an out label right here. Okay, so now we have our pins defined, and if we run LVS one more time, have to hit enter quite a few times just to make sure that we are getting past all the stuff that it's asking. Do we want to overwrite old runs? Do we want to close the old run? Things like that. But now, doing this run, unless we missed any other errors that I didn't see, this one should work very well for us. So it's taking a little bit of time to run. We can check the log file and see if there's still stuff going on here. But if we go all the way to the end here, let's see, it says Assura terminated normally. We may just need to stop this run. So if we can stop the run, close the run, maybe that'll help it. Maybe it just got hung up somewhere. So we're going to go ahead and run this. And this one should go very quickly. So now, much the golden thing that we want to see. So this tells us the schematic and layout match. And I like to double and triple check that my design can pass DRC and LVS. That way, if we're, for example, we make a slight change to pass LVS, we want to make sure that we're still within our design rules. So it's good to kind of double check and make sure that both DRC and LVS are passed with a current design. But from here, we can pretty much just press yes. So it tells us we have 0 DRC violations, but again, I like to manually check. And then it opens up this LVS kind of debug window, but since it matches, there's nothing really to debug. Now, there are a couple of other issues that we could have, and that's what I'm going to show you right now. So for example, if I delete this trace here, so now we have a floating source pin and a floating body connection here. If I try and run LVS, so before we saw that it was a pin mismatch because it didn't have the right pins matched to the schematic and the layout. But now what we can see is that we don't get a pin mismatch. We actually get, let's see, summary of errors. We have suggested terminal rewires and unmatched internal nets in our layout. So pretty much our layout has some issues. It suggests a terminal rewire, and it has 2 nets that are unmatched. And the reason that we have 2 nets that are unmatched is because whenever we broke the connection from our source to the body, we now, instead of having a source and body connected on the same net making up 1 net, we now have 1 net for the source, 1 net for the body. And if we scroll all the way up to the summary of errors here, what we can see is that we have the same number of devices, same number of pretty much everything else, but matched statistics for net, we only have 4 nets in our schematic and 5 nets in our layout. Okay? And then it's saying we have 1 unmatched net, 2 unmatched nets in our schematic and layout respectively. Now this gives us more information about the internal nets in our layout and in our schematic. It also tells us more information about what we may want to rewire, but you kind of have to dig and pore through this to figure out where exactly it is that things are falling apart. So problem schematic nets, it tells us it's the PMOS, G45, P1 SVT, the drain and source. So, so the body and then this DS connection because it's dual polarity. Those are missing a connection essentially. So these don't have an exact match. And the layout, we have 1 drain / source pin since it's symmetric and 1 body pin, 1 body net that's unconnected. So this kind of, it's not super direct in telling you what exactly it needs, but maybe we can use the debugger, although I'm not the biggest fan of the debugger here. So if we come over here, we can actually click this comparison. If we click on rewires, we could click open tool. So suggested terminal rewire, we could zoom to this rewire here to actually show where it is that something is unmatched. So this is showing it the device and the terminal here. So our specific terminal that we're looking at, if I zoom in over here, look at just this terminal, zoom to it, it's going to be looking at this terminal right here. Okay, so it's going to be looking at this terminal right here essentially. So we can also look at this layout net AVC3. We can zoom to it. It's going to be that's going to be this layout net up here. AVC5, zoom to it, that's going to be this unconnected net on our PMOS source, okay? So you can kind of use this in order to figure out where exactly you're missing a connection or where maybe you've made a short circuit. So for example, if I try to take a really convoluted route here, draw a path from this source down here, I'm pretty much shorting out a lot of stuff, right? I'm shorting out a lot of stuff and that's not going to be good at all. So now if we run LVS again, things together, it's actually taking the number of layout nets and reducing them because now we have a lot of stuff that is shorted together and it's creating 1 short. So now we can see we have 2 label shorts detected, so that just means that our input and output nets are shorted, which is true. They can follow a metal 1 trace from here directly to the output. And then we can also scroll up here and just kind of see there's unmatched pins, unmatched internal nets, unbound pins, because again, we have shorted pins together. It can create kind of a cacophony of errors. So problem layout nets that don't have a match in the schematic, this AVC1, if we open up the debugger, we can look for, so we can look at the inverter test system shorts, open the tool, and we can kind of use this to figure out, zoom into these different places, kind of use this to figure out where exactly we're getting all these shorted nets essentially, okay? So if we compare the two, we can take a look here, look at nets, open the tool, and what we can see in the layout, if we zoom to this problem net, it's kind of highlighting this entire blue net right here, and it's also highlighting the P substrate and things like that. And that's just because we have literally all of them shorted together. They're all forming 1 giant net, and it's saying this is where your problem's at. So you can kind of use this to help narrow things down a little bit. So I'm going to make sure I delete all of that bad net that I made. And now we're going to kind of go back to what we had before. So I'm just going to start off with a simple path from here up into this guy. And if I didn't get it aligned perfectly, which I definitely didn't, I'll close this run so we can kind of see a little bit more. This metal one isn't aligned perfectly. I can actually just press S and only shift this leftmost section, or sorry, this left up and down section in order to get it aligned perfectly. Okay, so now if we just double check, we can rerun DRC. DRC has no, press yes here to view the result. This is something that we want to see here. No DRC errors found. But like I said, we want to double check everything. So let's go ahead and run LVS. And now what we expect to see, hopefully, is that the schematic matches. So yeah, we're this golden screen right here that means that we've done a good job. This does kind of replicate our schematic. So I'm going to close out that debug window. Now, I want to show you a couple of other things that we haven't really had a chance to get to in this video because we're just working with a simple inverter. So if I add another NMOS, just for us to play around with. So if I add this other NMOS here, what we can see is that if I click this guy and select its properties, for this one, it opens up this attribute window first whenever we press Q, but we want to go to parameter here. So if we take a look at the parameters of this NMOS, we can see how changing the width to something like 240 nanometers, that's going to change the up and down width of this guy. And we have to apply first. And you can see that's changing the up and down width of this guy. And it's actually made it large enough to where we can have two contacts on our drain and source, which that's good. But we can drop this back down to 120 nanometers and press apply just to kind of see. So this is kind of our starting point here. Change the length in a similar fashion. Press apply. It actually gets physically, in my case, this would be wider, but the channel actually gets physically longer in this case. But we want to keep it simple, so we're going to stick with 45 nanometers. So length and width are very intuitive to see. However, the fingers can be slightly different. So fingers, what happens here is if we make fingers something like 3, we can press apply here. And what it's going to do is it's actually going to extend the number of, the number of gate connections that we have. So for example, if we needed to make something like a NAND gate where we need 3 NMOSs in series, we can actually use something like this because now we have NMOS A, B, and C, and there's only going to conduct current from all the way to the right, all the way to the left if all 3 of these are turned on. So this is effectively creating 3 NMOSs in series. Now we can also use this to create transistors in parallel. So for example, I'm not going to make this perfectly right because that could be kind of cumbersome right now. But if we have a route going up into here, and then this side is going down, this other side is going down. If this is our VDD net, this top one is our VDD net for an NMOS. So if this one is our ground net here, so if this is our ground net, then we can see we have one transistor that has its own independent drain, goes through the gate to ground. The second one also has its own independent drain, can go through this gate to ground. So kind of in a similar fashion, we could potentially add a ground connection here, and that would create 2 transistors in parallel. But you can kind of use this tool in order to kind of minimize the area of your layout as well. You don't necessarily have to make 3 individual transistors, and I'll go ahead and show you what I mean by that. So if I add an NMOS 1V, you don't necessarily have to, let me make sure the number of fingers is 1. You don't necessarily have to make one transistor here, another transistor all the way over here, and another transistor over here, because that's not very spatially efficient. So you can actually just use the fingers parameter here, change the number of fingers to 3, press apply, okay, and then now you have 3 transistors that you can kind of configure how you want to be connected, okay? Let me move this over just a little bit. Okay. So if we keep looking at these parameters, we can see we could add, we can play around with the gate connection, the folding thresholds, and things like that. We can see if we increase the number of fingers, the total width has now increased. And that's just because depending on how we connect it, it can change this total width, but this is just how Cadence defines it. We can also change a lot of other different things here. So this could be maybe simulation or extraction parameters. Source drain connection, we could have it to where it only has a source connection here, or yeah, so it connects sources together and things like that. So you can use this to maybe, you can use this to maybe improve your design slightly or have it do some things automatically for you. But this isn't necessarily what we're going to be using. So typically, if you need to do something really funky or really different, then what you can end up doing is you're pretty much just going to be using excuse me, you're pretty much going to be using things like this, okay? So keeping it simple, we can use the fingers, length, width, and things like that, and that's going to allow you to do a lot of different things. So for example, if we needed 3 NMOSs in parallel, or excuse me, 3 PMOSs in parallel, we could change this to, I'll bring it over so you can see, we can change this to PMOS 1V, set the number of fingers to 3 here, press hide here, and now we can set our PMOSs here. And we have to be a little careful with this, like I said, because we want to make sure that these 3 PMOSs are in fact in parallel. So what we could do is potentially add paths here going up, and of course this isn't the right width. Have 2 paths going up, and then these 2 connected together. And now what we can see is we have 1 transistor path. Oops, I accidentally opened help again. We have 1 transistor path that goes from source through the gate to drain. We have another path that goes from source through the gate to drain, and another one that goes from source to the gate to drain. So if these, for example, I'll add another path just to show what I mean. If these are connected together to something like a VDD layer, these can be all connected together as well to form parallel transistors. So you can get really creative with these layouts in order to make it as efficient as possible. But again, this is something that you're going to have to kind of experiment with and figure out what would work best. Now, the last thing that I want to take a look at is just kind of ways that you can improve your layout to make your life a little bit easier. Really quick, I just noticed this. We're going to stretch this up a little bit. Well, try as best as we can to get it to match here. And again, this is just kind of tidiness on my part. So one thing you can do to help your layouts kind of work for you a little bit more, it may actually be more beneficial if I can show you what you can do with this layout once we've created it. So once we have a layout that passes DRC and LVS, what we can do is if we needed to make something like a fan-out 2 inverter or something like that, we can go to our library manager. Like if we need to make a fan-out 4 for some reason, we can make a new cell view for fan-out 4, and it'll be a layout. And in this case, for a fan-out 4, we have 1 input inverter. The output is split to 4 different inverters, and then those outputs can be connected together, or they can be separate, things like that. But what we can do here is kind of like how we did it in our schematic. Instead of having to replace every single transistor, so for fan-out 4, it could be 10 total transistors. Of course, that doesn't seem too complex, but if you have something more complex like an ALU, CPU, then that can become very cumbersome. But what we can do here is actually use layout blocks that we've generated previously. So if we know, for example, I need an inverter in this layout, what I can do is I can open up the instance menu, and we're going to look in the library where we made our inverter layout previously, look for an inverter, and as long as we have made a layout for it, we can actually place this same layout into a larger structure here. So I can actually place this layout down, and if we press Shift F again just to show everything, now we have our input pin, our output pin, and we have our VDD, ground connections, things like that. So we can actually use this layout to form larger and more complex layouts. So if you're making something like a shift register, ALU, anything like that, you definitely don't want to lay out every single transistor because that is very, very cumbersome. What you want to do is start small with something like an inverter, NAND gate, AND gate, adder, something like that, and then slowly build your way up in both a schematic view, symbol view, and then also in the layout view, okay? So this is something really useful. But what we can see is that if we try to, for example, cascade 2 of these inverters back to back. So if I press C to copy, if I try to cascade 2 of these back to back, we can see we have to get them really, really close. And one thing that they don't really tell you in the design rules is that if you're going to have these contacts here, I'll zoom in just to see what you can see. If you're going to have these contacts here, you can't have them laid right next to each other like this. They have to be a standard size. So as a result, they either have to be right on top of each other or they have to be far enough away from each other. We can see that if we put them right on top of each other to try and pass one way, then we kind of get some things shorted together here. So that's not good. Like our output of our first stage is shorted to ground in this case. Whereas if we move this guy over to where it has enough space, now these things aren't connected. So this makes more work for us. We have to manually make these connections here. So one thing that you can do for simple layouts, if you're really trying to dedicate to it, is you can actually make it to where they have a fixed width. So what I mean by that is you can kind of define a width that you want your cell to be. That way you can just place an interconnect and you don't have to worry about connecting all these different things together, maybe just the input and output. So I'm going to go ahead and save this guy, We'll close it, and we're going to go back to our old layout, the inverter layout we were just working on. And if we take a look at this guy, press Shift F to see everything, we notice that these two guys are kind of lined up perfectly. And this guy's lined up perfectly with this left side here, but we want to have a little bit of extra width to it, essentially. And I like to think the little bit of extra width, I like to get it all the way out to this in-well layer, just because that makes it to where everything in this layout is kind of fit inside of this box. One thing we can also do, if we go to options here, hit display, we can make sure our pin names and instance pins are shown, because then that'll actually show our in and out here. So what we can do, I'm going to move this around just slightly, so maybe slightly down and over some. I'll do the same thing with this input pin, move it slightly down and over some. So we want to make sure that these are kind of bound in that same box as well. Now, what we can do here is we can actually extend this guy a little bit, either with a path or by increasing the size of our vias. But if we increase the size or the number of columns in our via, it may make it to where we extend too far out. So what we can do is on the inverter cell side, we can press P to add a path. And it's set to metal 1 layer right now, and the width isn't exactly right, but that's okay. We can fix that later. What you can see that we haven't quite seen yet too, and I haven't talked about, is this white bounding box. This pretty much shows us where our design rules limit us to be. So just like PCB design, there's a maximum or a minimum clearance in between two traces. So for example, if I try to run this guy next to here, it's going to say that it's a clearance violation because we're too close to this guy. So you can use these white boxes to kind of illustrate where your maximum distances are. So you can make sure here I'm perfectly fine. But anyways, we want this to extend all the way to the edge. I'll go ahead and press escape, and I'm going to click this guy, press Q, and I'm going to change its width to match the width of this guy here. So it looks like maybe it's about double, so I'll do 0.12, press apply. Yeah, and that's matched up pretty perfectly. Okay, so I can press Control D to deselect everything, and now this matches up pretty well with the width of the the in-well contacts, excuse me. So I'm going to add another path just like this, and we're going to extend it out to this right edge. I'm going to do the same thing, press escape, click this guy, and change the width. So 0.12, press enter. And then we're going to do pretty much the exact same thing down here for our ground connection. So I'm just going to click this guy, C, copy it, and I can just bring it all the way down to here, and it matches up just perfectly. Now, if we want to be really, really creative with this, what we can do is we can also extend out this contact as well, so this input pin, and we can extend it all the way out here to the right. Click this guy, change the width, 0.12, or whatever it is in your case. And then just for completeness, I'm going to add it to the output as well. So press P, extend this guy all the way out to the output. It's complaining about the minimum area right now, but because we're on top of this guy, we should be fine. And then, like I said, since we've used 0.12 so far, I'm going to stick with 0.12. Okay, so now while we're here, let's go ahead and just run DRC and LVS one more time, just to make good. We didn't violate any rules. So we can check our run. No DRC errors found, so that's great. And now we can close this guy and run LVS. So give it some time here. What we want to see is that our layout matches our schematic. So now we can just press yes here and close this guy because we already know it matches. Now, if I go back to my larger cell view, so say for example, I'm making an inverter and then I want to use this same inverter layout in something like a fan out 4. Then what I can do is I can go back to my fan out 4 layout, and you'll notice too here, all the changes that we made have propagated to this layout. So we don't have to reinstantiate it or anything like that. The changes we make in the lower cell do translate to the upper level cells as well. So now if I just want to cascade these, for example, what I can do is just Control C, or excuse me, not Control C, just press C. And now all I have to do is get these two things lined up perfectly together. So now if we just check out the metal 1 layer, for example, no view, everything except metal 1. Now our output is connected to our next input, and then this has an output on the next side as well. So if you're building something like a ring clock source or anything like that, this could be really useful. Or if you want to get really creative with it, you can have the output feeding this first one, and then you could have a multi-via stack up here. So just to kind of illustrate what I mean, maybe with a fan out 2 inverter, oh, excuse me, that actually wouldn't work here because we would have shorter connections. But for example, we can move this up and around, and this just kind of gives you a little bit more versatility if you have this kind of standard width and length. But this is, again, something that's definitely not required. It's just one thing where if you put a little more effort in the initial stage, just kind of goes to highlight a little bit of effort in the initial stage, making a really good layout in the initial beginning stage can really have a huge impact on how easy it is to integrate everything later. Okay, so just to kind of recap everything that we kind of saw that we have all these different layers here, and each one of them shows a different purpose. And we saw how we can use the DRC and LVS in order to check our designs. We also saw how we can start with a small layout here. So if I check again the small inverter layout here, we can interconnect these gates. We can create vias. Just to show too, if you want to have this going to a higher metal layer, you can create a via that goes from, if we want to make a stack, for example, we can go from metal 1 all the way to metal 4. And then we can check here. We have our metal 1 layer. Excuse me, we have a metal 1 layer here. So this is our metal 1 via, this little rectangle here on the end. We have a metal 2 portion, a metal 3 portion, and a metal 4 portion here. So this is actually going all the way up from metal 1 all the way to metal 4. And if you need to have something routed on metal 4, for example, this is a really good way that you can use that. So you can use the stack up tool in order to create that. Okay, but we've seen how we can use vias, how we can use paths in order to connect different things. We've also seen how we definitely, absolutely do need these in-well and P substrate contacts. Otherwise, it'll create a lot of errors, and that's something that's easy to forget. Now, I've also seen that you can use the DRC tool in order to kind of optimize how things are moved. So if you want to be maximally efficient in as far as space goes, you can use the DRC tool in that way. And then the LVS tool is just going to be showing you that your layout does indeed match the functionality of your schematic. So I hope I covered everything that we needed. I'm going to double check and just make sure we have covered pretty much everything that we need. So like I said, there's a lot of similarities to schematics, but the layout is typically a lot harder because you're working with these physical devices and you have a lot more rules and constraints that you have to follow. But this should give you kind of a general idea of how you can start with an inverter layout, definitely, but also how you can extend this inverter layout into something more complex like a NAND gate, and then from there you can grow into an adder, NOR gates, or creating all sorts of different things like this. So I hope you guys enjoyed the video. If you do have any questions, please feel free to let me know either in the comments or by emailing me. Other than that, thank you guys for watching, and I hope you enjoyed.